Hello and welcome to another video in which we seek to analyse and solve ordinary differential equations. I thought in this particular case I would do a lecture on a linear ordinary differential equation for the purposes of showing how to use a Wronskian to solve such an equation like this. Which is quite a powerful technique for linear differential equations, especially when only one initial solution is known and you can't find the other solution, because this will help you to find the general solution. Now, I've chosen this equation because it turns out there's a repeated root. So when we solve it, we just get effectively one of the roots, but repeated. Now, I'm just going to say a few things about this equation here, which we will call equation 1. So I'll just label that as equation 1 there. Now, we know if we solve this equation via normal high school mathematics, that the solution comes out to be y. In fact, we're working in terms of x, aren't we? So we know the solution is x equal to a t plus b times e to the t. Now, we know that's a solution, so at least that's something with which we can compare the solution we're going to get via the Wronskian to make sure that we're correct. So basically, normally with an equation like this, in an exam situation, you might actually be given one of the roots instead of having to work one of the roots out, either analytically or by trial and error. Now, you could use trial and error to work out the solution to equation 1, but I'm actually going to use high school methods to actually do that, so that well, it's a bit easier sometimes than trying to find a trial solution, because it's not always easy. It's not always easy to find trial and error solutions. And not unless you're prepared to invest a lot of time on occasions until you do find one. So if you can find the first solution analytically, then that is a better thing to do. So what we're going to do is we're going to say let me just change back to black. So we let x be equal to ae to the mt, and we'll call that equation 2. Now, we differentiate equation 2 to get x dot. I'm just using the x dot notation here instead of dx by dt, because it just condenses it a little more onto the page and we're not taking up as much space. So that comes out to be m-a-e to the mt, and we'll call that equation 3. We differentiate that again, and that comes out to be m squared a e to the mt, and we'll call that equation 4. Now, if we substitute equations 2, 3 and 4 back into equation 1, we get m squared a e to the mt minus 2m a e to the mt plus a e to the mt equal to 0. Now, straight away you should be able to see that the ae to the mt's just cancel, and what is left is m squared minus 2m plus 1 equal to 0. Right? Oh, we'll call this equation 5. Now, this is hopefully quite easy for you to solve. So we can factorise this quadratic equation out to give m minus 1 times m minus 1. For anybody who isn't sure, you multiply this out again, you will get equation 5. So basically, m times minus 1 plus an m times a minus 1 is the minus 2m, and the two minus 1's multiplied together, or minus 1 squared, gives the plus 1. So we know that we've got the right factorisation in terms of the brackets there. So that means that m is equal to 1 and or m is equal to 1. So it's a repeated root. Right, repeated root. So we just take obviously one of these. We take m equals 1, and we can now proceed to find the second solution, because if we go on to the next page, we say since one of the roots, m equals 1, then our first solution is x1 equal to a e to the t. I'll just explain that. What we had was, I'll explain that in green. So we had x equal to a e to the mt, if you remember. That's what we had here. I'll just come over here. So we had that, a e to the mt, and we substitute that m equals 1 back in for the m, right? So that's how we come to get a e to the t, because we've substituted 1 in for the m, and of course it should be an e there. So anyway, let me just get rid of that. Yeah. So anyway, let's just erase that, and we'll call that equation 6. So we've got equation 6 there. That's our first, one of our first solutions. So we know that's a solution to the to equation 1, and that it solves it. But let's suppose, and of course at this moment in time, we don't know what the second solution is. So let's write down the equation again. If I just go back, I'm going to write it down as x double dot minus 2x dot plus x. So we've got x double dot minus 2x dot plus x equal to 0. And I'm just going to double check that. Yeah. Right. Now, the Wronskian is actually equal to two things here. And I'm going to explain that. So to find the Wronskian of, we'll call this equation 1 again, because it's the same as equation 1, but just written differently. The Wronskian of equation 1 is equal to, I think normally they say it's some constant times e to the minus integral of p dt. I can't actually remember really if there is a constant there. So what I'm going to do is I'm just going to eradicate that, and I'm just going to write e to the minus p dt. And to be quite honest, it doesn't really matter, because you've got constants in the general solution anyway. So all the constants get combined in the end in any case. So we've got equation 7 here. Make it look more like a 7. Right. So we've got equation 7. Now what is p? Well, if we look at equation 1 here, we see that p is equal to this minus 2. So that is equal to P. Right, so the Wronskian is equal to e to the minus the integral of minus 2 dt. And that simply becomes e to the integral of 2 dt, which is simply e to the power 2t. That is our Wronskian. Yeah, we'll keep that as equation 7. So let's just outline that in red, because we'll need that. Now, the other way to find the Wronskian is to calculate the determinant of effectively the equation. So let me just show you how that is done. So we form this mock-up, as it were, as follows. So we know that one of our first solutions is a e to the t, but we don't know the other solution, so we'll call that x2, right? So this is our first solution, ae to the t, and x2 is a solution that we don't yet know, so we just call it x2. And then we differentiate ae to the t, and we get a e to the t. If we differentiate x sub 2, we get x prime sub 2, or x sub 2 prime. And the determinant of this here in the determinant signs is as follows. So you multiply this with this minus this times this, right? So what you get is a e to the t x2 prime minus a e to the t x2, and that is basically the determinant. But how does this help us? Because what we've got now is another differential equation. Well, let's write this differential equation down and equate it to what we have in the red box in 7, because these two determinants are the same. So this is actually equal to e to the 2t. Right, now we've got a first order equation that we can solve. So what we've got is, well, first of all, we divide through by a e to the t, and this gives us x2 prime minus x2 equal to e to the 2t over a e to the t, which, and the right hand side just comes out to be 1 over a e to the t. You know, you bring the e to the t into the numerator on top of the fraction, that becomes e to the minus t. E to the 2t times e to the minus t is e to the t. So let's go on to another page. So we've got dx2 by dt minus x2 equal to 1 over a e to the t. Let me just check. Yeah, I think that's right. Now, to solve, what shall we call this equation? Well, we'll call it equation 8. So we'll call this equation 8. Now, an integrating factor, that's what we want to find now. And an integrating factor of equation 8 is e to the power of minus 1 dt. And that comes out to be e to the minus t. So if we multiply equation 8 by e to the minus t, we get e to the minus t dx2 by dt minus x2 e to the minus t, and that's equal to 1 over a e to the t times e to the minus t. And of course, you can see that that cancels with that. And so what we're left with is e to the minus t dx2 by dt minus x2 e to the minus t equal to 1 over a. There. Now, the left-hand side can simply be written as d by dx of, in brackets, x2 e to the minus t. So basically, if you're not sure what we're doing here, you write this down multiplied by this. In this case, it's just all of this term, but really, you always take this kind of coefficient of the derivative and then multiply by the now that would be an independent variable, wouldn't it? No, x2 would be a dependent variable. I always get these mixed up. So you take e to the minus t and multiply it by x2, which is the dependent variable there. So we've got x2 e to the minus t equal to 1 over a. And we'll call that equation 9. Now, let's get my stylus because we're going to cut and paste equation 9. Add to new page, and we'll put that up there. Right, so integrating both sides, we get x2 e to the minus t equal to, and in actual fact, I've made some errors here, as you can see, because that actually should be a t, shouldn't it? There we are. Put a t in, and go to next. We need our eraser again. Oh, I can't get rid of that, but let's just, so there we are, t. So we're integrating with respect to t. So on the right hand side, that becomes 1 over a times t plus a new constant b. So x2 is equal to 1 over a t e to the minus t plus b e to the minus t. Now we know, well, first of all, we'll call that equation 10. We know that since x1 equals a e, in fact, I have to look because I can't remember. Yeah, x1 equals a e to the t. Then the general solution is x of t, make that look more like an x of t equals x1 plus x2, which is equal to a e to the t, and we'll put this b e to the minus t first. In fact, I've made a mistake there because that those should be plus t, shouldn't they? You take that e to the minus t to the other side of that equation, it becomes e to the plus t there and e to the plus t there. So we'll add that b e to the t on there plus the 1 over a t e to the t there. So let's cut and paste that. Okay, add to new page. So now that we've ironed out the errors uh, that we experience, so that becomes x of t equal to, well, we can take out the e to the t right throughout the right hand side of that. So what we get is a plus b plus 1 over a t in brackets times e to the t. So x of t is equal to, and how did I write the solution before? At plus b times e to the t. Well, it doesn't matter really what we call our constant, because we can call a plus b c1 and the 1 over a c2 t times e to the t. And what do we have the first time round? We had x equals at plus b times e to the t. So I'll just write compare with x of t equal to a plus bt e to the t. And I'm just going to double check that I have written that down. Yeah, I've made a slight, not really an error as such, but I've got the t the wrong way round. So where's my eraser? We just erase that there and put the t in there. So we're comparing two solutions, of course, they're the same. So the main reason why I've shown you how to find this solution via the Wronskian method is because we will be doing an equation. We will be solving an equation that is linear but does not have constant coefficients. So in the next video, we'll probably do that. So until then, I bid you farewell for now and hope to see you again, and take care for now. So thank you very much for watching and goodbye.